Howdy everyone, welcome back, and today we're going to talk about something a little bit different. We're going to talk about electric charges and electric forces. So first, what is an electric charge? So it's actually very analogous to mass when we talk about gravity. It's essentially how much something gets affected by electromagnetic fields and other electromagnetic effects. And just like gravity, the more charge I have, the more it gets affected, or the larger the force on it. And so why is this relevant? So most things are made of protons, which are positively charged, and electrons, which are negatively charged. So we'd think that a lot of things would be affected electrically, but I have a lot of things on the table here that would, if I had some charges and some electric fields coming in, wouldn't really be affected. That's because most things have a balance of those two things, and overall, they sort of spread out to not having an effect. But so when we talk about having a charge, there's the micro level and there's the macro level. So if I take a metal ball and I can actually give it a lot of excess charge. And usually if it's negative, I actually give it a lot of excess electrons, or if I make it positive, I took away electrons. So, okay, but what do these charges actually do? Well, they exert forces on each other. So it's kind of similar to gravity. Gravity, if you have two things with mass, then they'll pull on each other. They'll exert an attractive force and pull each other towards each other. So for electric forces, it's similar, but not exactly the same, because the difference is that you have two different signs of charges. For gravity, you can only have really positive mass as far as we understand. But for electrical things, you can have positive and negative charges. And so if you have two things of the same sign, you have two positive charges, they don't actually attract like gravity, but they repel. They push each other away. But if you have two things that are opposite charge, say a positive and negative charge, then they're attractive. So it's a little bit different. Some analogies though. So one thing to know about the electric force compared to gravity, and we'll see this in the math in a moment, is it's much, much stronger. So imagine I have a paper clip here and it's being pulled down by the entire mass of the Earth. It's pulling it down, but yet, with a magnet or something, I can keep that paper clip up. Like that much of a magnet is stronger than all of that Earth. It means gravity is actually really weak compared to the other forces. And so we can continue with the analogy with gravity here. So what does the force of gravity look like? Well, that's the universal law of gravitation that Newton gave us. And it's the force of gravity equals the mass of the two objects pulling each other over the distance squared times some constant. And this constant determines how strong this attraction is. So why is it 1 over r squared? Well, you imagine, the strength of this gravitational force goes out actually as a surface of a sphere. It's going out in all directions. And the surface area of a sphere goes as 4 pi r squared. So if it spreads out, it's just kind of like a balloon. When it spreads out, it gets weaker and weaker, just like a balloon's dye. Imagine you have a red balloon. It will get more diluted and wider. And it goes as the surface area of that sphere, r squared. So nothing magical here, but you can see how small this constant is, 10 to the negative 11. So let's compare that to the electric force. So the analogous force electrically is called Coulomb's law, and it looks very, very similar. The electric force equals some other constant, so this k, it's 10 to the 9, not 10 to the negative 11 now, times the two charges instead of mass over the distance squared. So the same thing, it spreads out in every direction equally, and then falls as the surface area of a sphere. Again, you can see how strong that the electric force is compared to the gravity. 10 to the 20 times bigger. That is insanely strong. And you can see how these problems are going to go. They'll be very similar. Instead of mass, we'll be using charges. We'll still care about the distance between them, use a different constant. But all this means is that we have a new force. Just like we had a spring force, just like we had a gravitational force, we can do Newton's second law problems just with the addition of this one force. And so let's do one of those. Okay, warning. So there's going to be math now. So if you don't like that, I don't know what to tell you, but it's coming. So here we have a picture. We have a lot of things going on here. So we have two charges, a positive charge and a negative charge. They're 9 centimeters away. We have one Q1, Q2. Those are some numbers that are up here. But this first charge is connected to a spring. That spring has pulled it, and the reason is I was connected to the spring and it was fine before, but I brought this additional charge in and it's now pulled it out of rest. So now this force, the spring, is going to be pushing this way and trying to resist that. And so this one has two forces on it, as the electric force that's attractive because they're opposite charges, and the spring that's trying to pull it back to its rest position. And this spring has been displaced 5 millimeters. And then what we wanted to know after all of these constants and all this stuff is how strong does the spring have to be? What's the spring constant? How do you do this problem? Okay, we see forces. We see forces. What should we think? What should we think? We should always think Newton's second law. That's the only thing we know how to do with forces. And all that's different here is that we have an electric force, which is something we may have not seen before, but it's going to enter Newton's second law the same way as before. Again, what is Newton's second law? The sum of all forces equals the mass times the acceleration of an object. What are the forces? Well, it's a spring force, an electric force. Okay, and what's the acceleration? Well, I should have mentioned this before, but this thing is now at rest. It's not moving, so it's not accelerating. The acceleration is 0. So these two forces have to be equal and opposite in this case. So this is going to put a limit, after we put in all the constants, of what the spring constant should be. Okay, and we break this into components. We break this, there's only one direction, so I'll break it in the x direction, whatever. And we noticed that the spring force was going to the left and the electric force is going to the right. They got to be opposite signs, so might as well make right positive, add a negative sign here. But what happened here is that we have this spring force, and we're using the approximation of Hooke's law, which hopefully, maybe we recall from before. We shove that in here. And then we have this new Coulomb force. And so they've given us the charge Q1, they've given us the charge Q2. We also know the distance, and this is just some universal constant, Coulomb's constant specifically. So we actually theoretically know all of these numbers, and we know this displacement x. The only thing we don't know is the spring constant. And so all we need to do is do some algebra and solve for that spring constant. So we move the spring constant to the other side, and we can divide this x and divide it over. And so now we have a side of all these things that we know. These are now just constants that we can put into a calculator. And if we do that, we find the answer is 5.2 times 10 to the 3. So again, some quick tips. If you're putting things in your calculator, I recommend putting things all in the same system of units. I'm going to say SI units, base units. The reason being, if I put the SI unit for every single thing in this equation, I will get out the SI unit in the end. I have to. So for distance, that's meters. So that would be for these two. And for these charges, that would be coulombs. So coulombs is a measurement of how much charge you have. And then here it'd be, it's Newton, meters, coulombs, it's a combination of those ones instead of centimeters or millimeters, because then you'll get something out that's not an SI unit in the end. So I know in the end, I can only get SI units. I should get newtons over meters. Okay, just a tip. Also, it usually helps to put all the numbers on at the same time. It's very easy to say this number divided by that number, and then you hit enter, and then you multiply that number, enter. But it's actually better to put them all at the same time, because if you make a mistake, you can just go and check. And I've made a lot of mistakes, just basic calculator mistakes, no logical mistakes, but just putting in the calculator wrong. Put in one thing wrong, and you get confused. So recommend putting them all at the same time in your calculator, or better yet, something like Wolfram Alpha, where you can visually see every term. Okay, so we're gonna have a little bit of a scarier question. Again, gonna just be electric forces. We see electric forces and forces in general, Newton's second law. So just a Newton's second law problem, but with some additional dimensions. So we have 3 charges now, charge 1, charge 2, and charge 3. And so they're all pulling and pushing on each other. Yeah, sure. So I could look at this and I want to find the total forces on any of them, how they move. That's a hard problem. And we'll save that. All we want to know is what's going on with charge 1 right here. What are the forces being exerted on charge 1? So what's happening to it? Well, it's being affected by charge 2, and it's being affected by charge 3. So if you look at charge 2, we know that these should repel, and they should only interact in this line. So it's either pulling it or repelling it along this line. So because of the same sign of charges, it has to be repelling. So the force of 2 on 1 has to look like this. We look at charge 1 and 3. These are opposite charges, so it has to be attractive again. It can only be in this line. So 1 could only be repelled or attracted, but they're the same charges, they're going to attract. So here are our 2 forces. That's a lot to be able to just write down these 2 ones. We have the force of 2 on 1 and the force of 3 on 1. Again, we could do that for any of these charges, but just because I'm interested in this one for the moment, that's what we'll look at. Okay, we're told the charges for all these things, we're told the distances for all these things, and the angles. So we should be able to figure it out. Okay, so what do we do? Where do we start? Well, it's forces, Newton's second law, write down Newton's second law. Let's do that. So we have Newton's second law written down here, And something we're going to realize that we need pretty quick are the magnitudes of these forces, and then we're going to have to break them into components. How do we get the magnitudes? Well, that is just straight up Coulomb's law. You have Coulomb's law for each of these. All we need to do for each of these, write down the specific charges, the charge for Q1, for Q2, for the force of 2 on 1, and the charge for 1 and 3 for the force of 3 on 1, and then the respective distances. And I think this was supposed to be 3, 1, but who cares? No one's paying attention here. So we can put all those numbers in. We're given all those numbers. That's now a calculator thing. We get the magnitude of the force of 2 on 1. So again, that's here in this, 0.5. And the force of 3 on 1, again, here, 0.288. That's because the charge of 3 is a little bit less. Okay, and we see that we have these two force vectors. Now we know their magnitudes. We're gonna have to now break them into components. This is why we've been practicing a lot of these things. Okay, so now we have the magnitudes of these forces, and now we have to break them into components. And this is where trigonometry and all that stuff is gonna have to come into play to be comfortable with that. So again, we explicitly write down Newton's second law, the sum of the forces, and again, that equals the mass times acceleration. But maybe this problem, I just want to know about the net force. But if I know about the net force, again, I can just write in, solve for whatever I want, as long as I know everything else. So what we do, we always break these down into components. I write an x version of the equation and a y version of the equation. Okay, and all I need to know is the x components of each of these forces and the y components of each of them. But again, this is just rewriting the same equation, but just in component form now. That's all that's happening. And so we look at the picture. That's going to inform us what the components look like. We look at the force of 2 on 1. Oh, we can see that's going to have an x and y component. So we're going to have to do a little bit of trigonometry. But the force of 3 on 1, well, that's only in the x direction, no y. So we look at that, and it's pointing in the positive x direction, positive at 3, 0 here, who cares? But here, how do we get this stuff? Well, we can see it's the negative x and y direction from here. It's pointing away from that. So both of these components have to be negative. And we draw out this triangle. So we have this triangle, 60 degrees here. The opposite side is the y component. So that's going to tell us that it's got to be the sine. If we write down the SOHCAHTOA again, sine of theta equals the opposite over the hypotenuse. So here's the opposite. We solve for that, multiply the hypotenuse the other side. We get here. Same thing for the x component. We get the cosine of an angle is equal to the adjacent over the hypotenuse. Here's the x component here. That is definitely adjacent to this angle. So multiply the hypotenuse the other side. No, here, cosine. Multiply the hypotenuse the other side has to be cosine, okay? And now these are all just numbers. They're all numbers. We can throw it in our calculator, write it out. We get, again, we wrote down these magnitudes above. We can put them in with their sines and cosines and straight write down all these numbers, add them across. Okay, x component 0.038 and y component negative 0.33. So does that make sense? Well, why would the y component be negative and way bigger? Well, you can see that there's only a net y component from this, so it should be negative. We can notice again the x components of these are kind of acting against each other, so they should lessen the total effect. So shouldn't be a big thing in the x direction. That makes sense, I think. Okay, so one thing we might want to know is the magnitude of the net force. So that is always just going to be Pythagorean theorem if we have the two components, which we just solved for. We have the x component of this final net force and the y component. That's what these were. Put that in the Pythagorean theorem, get out pretty much the magnitude was everything in the y. And I think that makes sense. Again, it's very little in the x, so it shouldn't really contribute much. I mean, that's pretty much all we can ask with these 2D charge questions. I can throw in a bunch more charges, but it's all going to be the same thing in the end. All these charges are going to have an attractive or repellent force. We write down the magnitude using Coulomb's law, write down Newton's second law, break it into components, write down all those components and add them together. It's going to be the same thing. It's very, very formulaic. It's going to be very similar every time. But we can see we could have done the same problem with gravity. And the only thing that's different now is we have charges and they can be repellent or attractive. I hope you can see that we're not asking to do anything more than potentially with gravity. All we're doing is a Newton's second law problem in a different context, maybe in 2 dimensions, maybe with electric force that has attractive and repellent components. But it's just a Newton's second law problem. So if we're comfortable with that, we should be comfortable with this. And again, it's going to help to work out and think about this sort of problem more. Okay, that's about all I have Thanks for watching. If you have any questions or thoughts, feel free to let me know. Okay, but good luck. See you next time. Bye.